Okay, so again, I just sent the announcement about the, what do you call it, the homework. Okay, let me get started with this. Okay, so again, I emailed the notes to you, so you should have it in your inbox. All right, so I think I might have actually said this last time, but I feel better going through it again. We saw many different ways of getting the domain of a function. And one of them was if you have an equation. Remember, that is, you can define a function using an equation in x and y. Basically, what you do is, to determine if it is a function, you have to sketch its graph. Remember, we're trying to see if y is a function of x. And what we're doing, to figure out if you have a function from the given equation, you sketch the graph in the Cartesian plane. It's a little bit easier to do that because, we have graphing software like Desmos. Desmos, GeoGebra, stuff like that. And if that graph passes the vertical line test, which again means every vertical line you draw will intersect the graph at most one time. Or in other words, there is no vertical line that can intersect the graph more than once. Maybe it won't intersect at all, but it can't intersect the graph more than once. Then you have a function. And then you can get the domain of, the function if you have from the equation in x and y. I mean, what you really want to do first is try and get y in terms of x. That may not be easy to do, if even possible. I mean, not in this class, but in other math classes, you'll actually encounter that, where you can't get y in terms of x. But we're not going to look at that now. And basically, when getting the domain, we have these rules to follow. The denominator is never 0. In other words, the denominator has to be non-zero. You never divide by 0. You never take the square root of a negative number. Okay? Since we're not dealing with complex numbers, you never take the square root of a negative number. In other words, if you have the square root of something, I have an example down here, we'll see some today. If you want the domain, what you want to do is you want to figure out when the radicand, what you're taking the square root of, is non-negative. Now, if you happen to have, though, that square root in a denominator, like 1 over the square root of something, okay, w is that something, then you have to determine when that w is strictly greater than 0. That's really what I'm saying here. So you could think of 3 as almost like a special case of number 2, really. So that's what we have here. So as an example, just to get started, so to say, although I think I might have done this last time, but if you have 1 over x, right, we saw that we do have a function from this equation. I did sketch the graph before. It was actually the last graph in the last set of notes I just sent you. But it does pass the vertical line test. The domain here is all x, such that the denominator is non-zero. So in other words, it's all x that are non-zero. This one, okay, we can't take the square root of a negative. And since this is not in the denominator, we only care about when x, which is the square, what you're taking the square root of, is non-negative. Right? We can allow x to be 0. You get the square root of 0, and that's okay. So the domain is this interval, all x such that x is non-negative, which is the same as this interval. The notation in the book might be a little bit different. They might use different notation when specifying the domain. If you stick with my notation, that's fine. Now, I'm not going to test you on material at all that I do not go over. I just personally don't think that's fair at this level. So, okay. So here's an example. Now here we have the square root is in the denominator. So in this case, we want to know when the radicand, which is 2x minus 4, is strictly greater than 0. Right? We can't allow 0 here because we'll be dividing by 0. So because of that, we have this. This is strictly greater than 0. Okay, that's cool. So let's do it. So again, we have this inequality to solve. So we're using what we have learned in 1.5. So we have 2x minus 4 greater than 0, right? We add 4 to each side. You know, it's just like an equation. You want to get x all alone. And that's what we're doing here. Get the 4 out of there by adding. What you do to one side, you do to the other. Keep it balanced. We have 2x greater than 4. From here, right, we don't want 2x, we want x, so we divide both sides by 2. The inequality we leave alone, right? You only flip, you know, that is, you only turn the inequality around if you're multiplying or dividing by a negative. That's not what we're doing here. So we end up with x greater than 2. So the domain is all x such that x is greater than 2, which as an interval is this. Okay, now before we do some more examples, I really want to actually make a mistake. Are there any questions on this? Remember, I can't see the chat, so if you have a question, use that hand raise feature. Or just speak into your mic. Actually, use the hand raise feature. That might be better. Okay. Now, before we do more examples, these are just certain examples of functions that you will encounter in math. We have a polynomial function in x, excuse me. And that's a function that looks like this. You have f of x equal to something like this, a polynomial. Remember, this is the form of a polynomial. So n is the degree. These a sub n's, remember, these numbers in front, these a's, subscripts, those are numbers, those are constants. Now, the domain of this, it's actually very easy because the domain is all real numbers. The range, well, that's a different story. It turns out that the range depends on your degree. It turns out that the degree is even, the range is not going to be the same as the domain. If the degree is odd, then it will. That's a different story, though. That takes more math tools, so to say, to prove that. But so we're not going to prove that here. When n is 2, we get what's called the quadratic function. We're going to see how to graph that in chapter 3. You'll graph it by hand, that is. I know we have Desmos, GeoGebra, but you really should be able to graph it by hand. You can't always depend on the calculator. Now, if n is 1, we get a linear function. We get a line, straight, non-vertical line. Okay. Now, if you have p of x over q of x, so p and q here are two polynomials, polynomial functions. Okay. This is actually what we call a rational function. A rational function. One polynomial over another. And the domain is all x such that the such that the denominator is not 0. Right? Again, we never divide by 0. We're not going to graph these functions. You learn how to graph those in, I want to say, pre-calculus, 105, Math 105. The book goes into how to graph it, but we're not going to do that. To find the domain, what you want to do first is solve this equation when the denominator is 0, and those are the numbers you're going to throw out, so to say. In other words, the domain will be all numbers except the solutions to this equation. And solving this equation can be tricky. If you have a polynomial of degree 2, you can use what we have seen already. The quadratic formula, you can see factoring. If it's higher than degree 2, then it can be a little bit, it can get really tricky sometimes. Okay. This, we have seen this, the square root function, the square root of x. The domain of this, we just did it on the other slide, is this interval, all x, such that x is non-negative. The range is actually the same. Remember, the range is all the outputs, all the f of x's, so to say, different x's, all the outputs. It turns out the range of this is the same as the domain. Okay. So here's another example. Let's say we want to find the domain of this. So really we have what we just saw. We actually have a rational function here. Non-zero constants are polynomials. Actually, let me say it again. Constants are technically polynomials. 1 is a polynomial, degree 0, but it's still a polynomial. But we want to know when this denominator is not 0. That's the domain. Let's first see when it is 0. That's what I'm doing here. On a quiz or exam, if I don't tell you what method to use, you can use any method you want. I'm factoring, okay? So here we have x squared plus bx plus c, where b is 2 and c is 1, okay? So we want two numbers whose product is 2 and whose sum is 1. Wait, check that. Sorry, backwards. We want two numbers whose product is 1 and sum is 2. Sorry, I got that backwards. And 1 and 1 are the ones that do it. The product has to be 1, the sum has to be 2. And 1 and 1 are the ones that pull that off. So in other words, we have this is equal to x plus 1 times x plus 1, which is x plus 1 squared. So the only way this could be 0, right, is if this is 0. So what we do is we solve x plus 1 equal to 0. And so that's not so bad. You just subtract 1 from each side, you get x is negative 1. So the domain of this is all x except negative 1. All right, let me pause the recording.